welcome to our lesson on chord theorems. So there's 4 theorems we're talking about today. The first one is what happens with congruent chords and their intercepted arcs. So in the same circle, or if you had 2 congruent circles, 2 minor arcs are congruent if and only if their corresponding chords are congruent. So if chord AB and DE are congruent to each other, then the arcs AB and DE are congruent to each other as well. So in our first example, we're solving for x, and we see that this chord over here is 115 degrees, and this chord over here is 115 degrees. So based on that, we know that this chord and this chord are equal to each other. So now if I want to solve for x, all I need to do is set those 2 expressions equal to each other, and then solve for x. So pause the video now to find out what x is equal to. If you got x equals 9, you are correct. And in our second example, we want the measure of arc EG. So we know that FE and FG are congruent to each other because they are marked, which means that this chord EF and the chord GF are also going to be equal to each other. So it says that EF is 135, which means FG is also 135, and we are looking for this missing arc here. So remember that if I add up all of the arcs in a circle, it will always equal 360 degrees. So that's what I'll do to solve for x. You could, of course, solve this a little bit differently. You could just add the 135s together to get the 270 and subtract from 360. You do not need to set up an equation. But if you're practiced in solving equations, it makes it easier when you get to something where you have to use an equation. Our next theorem is for the perpendicular bisector of a chord. So the perpendicular bisector of any chord includes the center of the circle, which means if we wanted to draw the full perpendicular bisector within the circle, it would be a diameter of the circle. So here we have our chord FG, and if KH will be a perpendicular bisector, then it's going to include the center here, which means that this would be a diameter. If we were just talking about from J to K or J to H, it's a radius. But this actually ends up being helpful. If we ever wanted to find the center of a circle through constructions, this is a theorem that we would use. In number 3, we have that JM bisects HI. So before I do anything, I'm going to add those dashes onto HI so I know that those 2 pieces, HL and LI, are congruent to each other. If JL equals 2, so JL is right here, and NM equals 17, what is the length of HI? So it seems like we don't have enough information to go on right now. We have the 2, which is just this tiny little piece of that diameter. It doesn't do a whole lot for us. And we have that MN is 17. So remember that if we're only going from the center to the edge of the circle, we have a radius. And any other line in that circle that went from the center to the edge would also be a radius. So because I know that JM is perpendicular to HI, I have my right angle at L, I could add in my own radius from N to I, and I know that that has to be 17. So NJ also has to be 17 because just from N to J is another radius. So if all of NJ is 17 and that tiny little piece of JL is 2, I can subtract that and I'll get 15 for LN. So then I have a right triangle, which means we could use a squared plus b squared equals c squared to solve for Li. So then if I have a squared plus b squared equals c squared, I could solve for Li. 15 is one of the other legs. I can substitute that for b. And 17 is my hypotenuse, which could substitute for c. So you can go ahead and do Pythagorean theorem, or if you've memorized your triples, then we know that Li must equal 8. And remember, we wanted the length of HI. So HI would be the whole thing, and both pieces are congruent to each other. So Li is 8, and LH is also 8. So 8 plus 8 would make 16. So HI equals 16. Number 4, if MN is the perpendicular bisector of PQ, and PQ equals 16, and OL equals 6, what is the length of MN? So perpendicular bisector again, we're going to have those 2 pieces that are equal to each other. from P to Q is 16. If P to Q is 16, how much is P to L? Right, so this would be 8, because both of those pieces would have to be 8 to make 16. OL is 6. And just like in our last problem, if I want to find my other missing piece, I can connect from O to P and add in my own radius, which also happens to be a hypotenuse of this right triangle. So because of our right triangle, we could use Pythagorean theorem to solve for the radius. So 6 is one leg, 8 is the other leg, and we're looking for OP. And perhaps you recognize this triple, 6, 8, and what's missing is 10. And remember, if you don't have your Pythagorean triples memorized, it's fine. You can always just go ahead and actually figure out Pythagorean theorem. So OP is 10, and what we're actually looking for is the length of MN, and MN would be a diameter where OP is a radius. And remember, if you want your diameter, you just have to double your radius. So for our final answer, we are getting that MN equals 20. Our next theorem is for the chords that are equidistant from the center. If two chords are congruent, then they are equidistant from the center. So here we can see that KL and MN are congruent to each other, and we're just getting that from down here. And if that's the case, and we were to add a perpendicular segment from Q to the center of the circle, and we were to do the same thing from KL using P, then we're going to end up with these two pieces, OP and QO, that are congruent to each other as well. So you might be familiar with a saying that the shortest distance between any two objects would be a straight line, but that's not just any straight line. It needs to be a line that's perpendicular. So that's why we're going to see the 90-degree angles with problems like these, just to verify that this is the shortest distance possible. So anytime you have congruent chords in your circle, the distance from each chord to the center would also be congruent. So in example 5, RS is congruent to UV. Solve for X. So remember, if those chords are congruent, then these distances from the center are congruent to each other. So to solve for X, we simply need to set X squared equal to 9. If you said X equals 3, then you are correct. Number 6, find the length of WX. In the diagram, they're showing us that these lengths are equal to each other, and that allows us to conclude that these two chords are equal to each other. So if we want to solve for X, we simply need to set them equal. Pause the video now so you can find X. And don't forget to plug in for WX. If you got that X equals 9 and WX equals 12, you are correct. Here's our last theorem, the parallel chords theorem. If chords in a circle are parallel, then they intercept congruent arcs. So as long as RS and UT are parallel to each other, then the arcs in between them are congruent. Which means that this right here needs to be edited. It should be that RU is congruent to ST. Please note that RS and UT are not necessarily congruent to each other. And you can see that in the examples. Like right here, this chord and this diameter, they're definitely not equal to each other. They are two different sizes, but they are parallel, which means that we're going to have these arcs in between them that are congruent. So we're going from having parallel chords to congruent arcs. I like to relate this to food. Think about how an ice cream sandwich looks from the side. Right, so you have your cookie, you have the ice cream in the middle, and then you have a cookie on top. Ideally, those two cookies are parallel to each other. Have you ever tried to bite into an ice cream sandwich where the cookies were not parallel? Where you have a cookie on the bottom, and maybe you have like a little bit of ice cream on the left, but then a whole lot of ice cream toward the right. And so the top cookie does not sit parallel to the one on the bottom. You try to bite into this side, and then all the ice cream kind of goes out the other end, which is not what you want with an ice cream sandwich. You want the cookies to be parallel so that everything is nice and even in the middle. So let's get to these examples. Number 7, we want to find the measure of arc BC. BC's over here. Why don't we mark that with an X? I definitely forgot to add the parallel symbols on the circles, so forgive me for that. But AB and DC are parallel, which means that if BC is X, AD is congruent to that, so AD would also be X. I know about my other two arcs that AB is 124 degrees and that DC is 86 degrees. So now all I need to do is write out my equation so that I can solve for X. And remember, all the arcs in a circle add up to 360 degrees. Pause the video now so that you can solve this equation. In number 3, if you got that the measure of arc BC equals 75, you are correct. Okay, so for number 8, we have our two chords that are parallel to each other, which means that we know that these arcs in between them are equal to one another. So if my arc that I'm seeing on the left is 2x, the arc I'm seeing to the right is also 2x. We know that our arc up here is 30. What equation would you write to solve for x? There are two ways to go about this. Remember that anytime you're seeing this line that goes through the center of the circle, you know that you have a diameter, and your diameter cuts your circle in half. So you actually have a semicircle here with the 2x, the 30, and the 2x. So I can set up an equation that it's 2x plus 30 plus 2x equals 180. This is not the only equation that you could solve. You could also set it up so that you have 2x plus 30 plus 2x plus 180 equals 360. Whichever equation that you like, go ahead and solve now to find x. No matter which equation you set up, you should be getting that x equals 37.5, and if that's what you got, then you are correct, and this concludes our lesson on chord theorems.